Hiya, I'm back, and on to part two of our double lesson extravaganza um, as far as solving free variable linear simultaneous equations is concerned. Part two is a little bit more visual, hence the diagram in front of me now. What you are looking at are the 5 different situations that can occur when you try and solve 3 variable linear simultaneous equations. When you're solving a 3 variable linear simultaneous equation with 3 equations, you are actually looking at 3 planes, and the 3 planes are configured in space in one of 5 different ways. These are those 5 different ways, and what you need to understand is that when you go to solve simultaneous equations, 3 variable simultaneous equations, you will be in one of these situations, and you need to know which one you're in from what happens when you go to try and solve them. Now, if we were solving using an inverse matrix, what we did earlier in the week, then you would find that the determinant would be 0 when there is not a unique solution. So if the determinant is 0, you can't find the inverse matrix because you can't go back to where you started from, and therefore you get you can't solve the equation. If the determinant isn't 0, then you can find the one unique solution. So that's great. Okay, so we can't solve it if the determinant is 0. But does that not mean we don't care about what's actually happening? No, we do care. We'd like to understand why we didn't get a solution. And it's because we're in one of these 4 situations here. It's either that the 3 planes just lined up parallel like that, so there's nowhere where you can be on all 3 planes at the same time. It could be that 2 of them were parallel, the other one wasn't, in which case, once again, you can't be on all 3 planes at the same time. It could be that none of them are parallel, so they do kind of intersect, but they don't all intersect each other at the same point. So 2 of them intersect each other somewhere, and then another pair intersects somewhere else, and another pair intersects somewhere else. When that happens, you make a kind of a sort of a triangular prism sort of shape in the middle. It's quite good if you can actually see these moving, so you can see what I'm on about. You always get this kind of triangular prism with sort of 3 rectangles and a triangle on the end. Of course, this is infinite, so it's not really like that, but if you can imagine it, you get this triangular prism. And again, there are no solutions. There's nowhere where I can't stand on all 3 planes at the same time. The really interesting one, though, is this one here. Because this one here, you can stand on all 3 planes at the same time, but in different places, anywhere along this line. This is called a sheaf of planes. And you can tell from the equations which situation you're actually in. So I've tried to summarize it here, but I'll show you on the notes exactly what's happening, and from the integral notes. But for example, if when you write out the 3 equations, the left-hand sides of the equations are all the same, so the same x, the same y, the same z. All right, you might have to divide through by a factor to make them the same, but you can make the left-hand side have the same x, the same y, and the same z for each of the 3 equations, and then a different number on the right. You're in that situation there. If you can do that for 2 of the equations, so for example, you could get 3x plus 2y plus z equals 10, and 3x plus 2y plus z equals 5, and then something else for the 3rd equation, completely different, then you're in that situation here. Oh, incidentally, the fact that this is all sort of perpendicular is just for convenience. So the the third plane doesn't have to be perpendicular to the other two. It could just be on a different slant. It just makes it easier, I think, to draw these diagrams. Obviously, I just nicked these off the internet. Okay, so so you might be asked in the exam to describe the situation that you were in. So it's important you understand that about when you can tell when you've got 3 parallel planes or 2 parallel planes and a non-parallel plane. Okay, so you can talk about that. And if you can't manipulate them to be like that, then you must be in one of these 2 situations here. So you check to see if you're in that situation there. Then you check to see whether you're in this situation here. And the way you check to see if you're in this situation here is by eliminating one of the variables, maybe the z, by writing the third equation with z as the subject, and then subbing that into the other 2 equations. And if, having done that, the 2 equations end up exactly the same, then you're in this situation here. Okay, and you can then write out the equation of that line. I'll come back to that and how you actually write the equation of that line out once you know you're in that situation. Okay, and that's it really. If you're not in that situation, you're in that situation. If they weren't parallel and that didn't work, the 2 equations didn't turn out the same, then you're in that situation there. Okay. One more thing to say. Another word you'll hear bounded around is equations being consistent. Okay, and or inconsistent. And for the diagrams here, we say that they are consistent in these 2 cases, and they're inconsistent in these 3 cases here. Consistent just means there is at least one solution somewhere for the 3 equations. They kind of make sense together. They can all be true at the same time is effectively what that is saying. All 3 equations can be true at the same time. And they can in these 2 cases, they can't in these 2 cases. So that's the basic idea of this. If I come over to the notes here, okay, they basically explain in words down here what I've just explained to you. Okay, so you can read that for yourself. But then there are some examples, 3 examples, leading to different situations. So I just wanted to not do them fully, but just run through those so you can see what's actually going on. So in the first equation, a bit boring this one, you just end up with a unique solution. Okay, so that's the case 5, the one solution case. They've done it with an inverse matrix. Of course, we could have done it with row echelon form if we'd wanted to now. Okay, by writing an augmented matrix and doing that ones down the leading diagonal thing that I showed you. So now the second one. So they start the process off, and it turns out that when you work out the determinant, it comes out, for this matrix here, it comes out to be 0, so they can't find the inverse matrix. Alright, at that point the alarm bells are ringing. Oh my goodness, we don't have a solution. Or do we? Or do we just not have a unique solution? So, in order to do that, you have to eliminate one of the variables from the other 2. So they've chosen to actually eliminate the x from the second one by subtracting one lot of the first equation from the second equation. Remember, I said I said earlier you could get rid of the z, but it doesn't have to be. So they've got rid of the x in the second equation by subbing the first equation into the second equation effectively, or if you like, taking one lot of the first equation away from the second equation, a bit like what you do with row echelon. If you do that, you end up with the second equation being y plus 2z equals 1. Hang on a mo. That's what the third equation looks like. Therefore, there are an infinite number of solutions, and we have a sheaf of planes. You can just find a value of y and z that work in here. For example, y equal to 0 and z equal to 1/2. And then you can sub that back into the other to find the value of x, and you've found a solution. However, it's not a unique solution. You could buy any pair of y and z that work in there, sub it in to find the x, and what you're doing is you're finding a line where the sheaf of planes all intersect. Okay, we'll come on, explain in a minute how you write your final solution to that. That's at the bottom of the page for some reason. They could have done it there, but they do it at the bottom. Now in this third case here, okay, again the determinant's 0, so no go. Okay, and in this case, we end up with, so we try and do the same trick as we did on the second example. We try and eliminate a variable to find out whether or not the equations are consistent, and which has got in the sheaf of planes, but it doesn't work. So to do this one, they subtract 2 lots of the first equation from the third equation to eliminate the x, and 2 lots of the first equation. What am I doing here? Subtract 3 from 2 lots of 1. Like that. So 3 from 2 lots of 2. Like that. All right. Okay. So they're eliminating the x from the second 2 equations, and you end up with 2 equations that are not the same. Therefore, it's not consistent. Okay. So in that case, we're in the triangular prism situation and not the parallel. Remember I said about these here, and we're not in that situation because it was not possible to write any of the original equations so that the left-hand sides were the same, with the right-hand sides being different. Okay, it doesn't matter that these have the same left-hand side. That's not the same thing as what I was saying earlier. Finally, the sheaf of planes was actually the second example here. If you want to write out the actual equation of the line, then you choose a parameter, lambda, say, to stand for one of the variables, say z. So if we say that z is equal to lambda, and then we substitute that back through to find the value of the other variables, okay, and that will, so we can sub into, because we've done some work with the y plus 2z equals 1, we could rearrange that to say that y is 1 minus 2z, so y is 1 minus 2 lambda, and if we sub both of those into any of the 3 original equations, we can find that x is 1 plus lambda. So this is a equation of a line written using a parameter in equation of a line in 3 dimensions, and that's how they'd probably want you to write the final equation of the line. Of course, there, as you know from vector work, there's other ways of writing the equations of lines in 3 dimensions, but that's the one that you probably use. So that's it, really. You just need to, that hopefully means you can do some more of the exercises, or at least give them a go, and we can perhaps come back together and have a chat about that. Maybe we could have a bit of a Zoom lesson on Friday and just come back together and just have 10-15 minutes discussing all of this. Well, I'm thinking in my head here, so we'll come back to that later when I've thought a little bit more. Now, the other thing that I want to show you, I don't know if I can show you on here. I'm not sure this is quite how technology is supposed to work. If I go to the classroom, I haven't actually set the assignment at the time of writing this, but you will have by the time you're reading it, because you're looking at it now, if that makes any sense. Okay, so on here you will see, you won't see, right, ignore that, I'm just going to tell you. I have sourced on the internet, I'll tell you what, I'll do it on here now. On the internet, here it is, I've put a link to this rather fantastic page here, which allows you to actually sub in or manipulate. It doesn't work very well on an iPad. In fact, it doesn't work at all on an iPad. So you might, if you're only using an iPad, you might not be able to do this. Oh, that's great. It works great on a computer, but not on my iPad. If you can get it to work, that's great. If you've got a computer, do it on there. But you can actually slide these, and these are the coefficients of the 3 variables, and you can see the actual planes moving around on the screen. It's rather cool. So you'll be able to check the situations for each of the questions that you get asked. I've no idea if you can do that on your fancy dancy calculators. I'd imagine it's a little bit beyond even your calculators, but I don't know. You know more than me about those. But have a little play on that. It is quite cool to see, although like I say, it doesn't work very well on an iPad. It works great on the computer. How the different equations plotted as planes interact with one another, and you can get to see all these different situations and have fun with that. This is actually an exercise where they're expecting you to manipulate them to try and get all the different cases here. But well, you need a lot of time on your hands if you're gonna play about with that. But anyway, it's there. Have a little look. Hopefully, it'll increase your understanding of this topic. And then, in theory, once you've done all this work, we've covered matrices, and obviously we can start talking about looking at doing the assignment. I'm not planning to move on to Maclaurin's expansion until the second lesson next week. So we have got time to consolidate all of these ideas. Just go away, try the exercises, have fun. If you run into difficulties, just give me a message and I will try and help you. Okay, that's me done for now. So see you again soon.